Welcome to this coding walkthrough. In today's session, we will solve problem number 1207, unique number of occurrences. We'll explore different approaches to tackle this problem and analyze their time and space complexities. Let's dive in and break it down step by step. In this problem, we are given an array of integers, and our task is to determine whether the number of occurrences of each unique value in the array is distinct. In simpler terms, no two different integers in the array should have the same frequency of appearances. If all the frequencies are unique, we return true. Otherwise, we return false. For instance, an array might have some numbers that occur multiple times, and we need to check if none of those counts are repeated. The input will be a one-dimensional array of integers, where each integer is constrained between -1000 and 1000, and the length of the array can go up to 10,000. The output will be a Boolean value, either true or false, based on whether the condition is satisfied. Let's look at an example to understand this better. Suppose the input array is 1, 2, 2, 1, 1, 3. Here, the number 1 appears 3 times, the number 2 appears 2 times, and the number 3 appears 1 time. If we list these frequencies, 3, 2, and 1, we can see that they are all unique. Therefore, the function will return true for this input because no two numbers share the same count of occurrences. This demonstrates the core requirement of the problem, where all the frequencies must be distinct. Now, consider another example where the input array is 1, 2. In this case, the number 1 appears 1 time, and the number 2 also appears 1 time. When we observe the frequencies, both values have the same count of 1. Since the frequencies are not unique, the function will return false. This highlights the situation where the condition is not satisfied, demonstrating that the output depends entirely on the uniqueness of these frequencies. Here's another example to further clarify. If the input array is -3, 0, 1, -3, 1, 1, 1, -3, 10, 0, we can calculate the occurrences as follows. -3 appears 3 times, 0 appears 2 times, 1 appears 4 times, and 10 appears just 1 time. The frequencies are 3, 2, 4, and 1. Since all of these numbers are distinct, the function will return true. This example illustrates how the problem handles both positive and negative integers, as well as 0, and still focuses solely on the uniqueness of the frequency counts. Finally, let's explore some edge cases. If the input array contains only one element, such as 7, the frequency is just 1, which is unique, so the output will be true. Similarly, if all elements in the array are the same, like 5, 5, 5, 5, there is only one frequency, 4, which is also unique, so the output will still be true. On the other hand, if all elements are distinct, as in 1, 2, 3, 4, each value occurs exactly once, and the frequencies are unique, resulting in true. Lastly, for a large input like 1*10,000, where the number 1 appears 10,000 times, the only frequency is 10,000, which is unique, so the output is true. These examples help solidify our understanding of the problem and how it applies to different scenarios. To tackle this problem, we considered two main approaches. First, the brute force approach is quite intuitive. The idea here is to count how many times each element appears in the array by looping through it and storing these counts in a dictionary. Once we have those frequencies, we then check if all the frequency values are unique. For instance, we could extract the frequency values into a list and compare its length to the length of its set version. Since sets only store unique values, any duplicates in the list would result in a mismatch in lengths. However, this approach is not very efficient. It involves multiple passes through the data and redundant operations, especially when checking for uniqueness in a naive way. As a result, this leads to a time complexity of n squared, making it impractical for larger datasets. To address the inefficiencies of the brute force method, we turn to the optimized approach, which leverages hash maps and sets for greater efficiency. Here, we use a hash map, or dictionary, to count the frequency of each number in the array in just a single pass, giving us an n time complexity for this step. Then, we extract the frequency values from the hash map and store them in a set. Because sets only store unique values, we can determine whether all frequencies are unique simply by comparing the size of the set to the size of the frequency list. This eliminates redundant checks and improves overall efficiency. The key insight here is that the problem is really about frequency uniqueness, not the specific values in the array. By separating the problem into counting and then validating uniqueness, we simplify the solution. While the optimized approach does use more space, with a complexity of O(n), due to the hashmap and set, this trade-off is worthwhile because it significantly reduces time complexity to O(n), and scales well for large datasets. This makes it the clear choice over the brute force method, which is slower and less practical for larger inputs. In this problem, we need to determine whether the frequencies of elements in a given array are unique. This means that no two elements in the array should have the same frequency of occurrence. To solve this, we can break the algorithm into clear steps. First, we initialize two data structures, a dictionary called frequency_map to store the frequency of each element and a set called scene_frequencies to track the unique frequencies we encounter. A dictionary is ideal for this because it allows efficient O(1) insertion and retrieval of frequencies, while a set helps us enforce uniqueness efficiently. Once these are ready, the next step is to count the frequencies of elements in the input array. As we traverse the array, for each element, we update its count in frequency_map. If the element is not already present, we start its count at 1 using the .get method with a default of 0. If it's already present, we simply increment its count. This ensures that frequency_map accurately reflects the frequency of each element in the array. Once we've completed counting frequencies, the frequency_map dictionary will contain each unique element as a key and its frequency as the corresponding value. With this information, we can now check whether these frequencies are unique. To do this, we iterate through the values in frequency_map, which represent the frequencies. For each frequency, we check if it already exists in the scene_frequencies set. If it does, this means we've found a duplicate frequency, so we return false. Otherwise, we add the frequency to scene_frequencies and continue. If we finish processing all frequencies without encountering duplicates, we return true, indicating that all frequencies are unique. It's also important to consider some edge cases. For example, an empty array trivially has unique frequencies since there are no elements. Similarly, an array with a single element, or one where all elements are identical, will have frequencies that are inherently unique. However, arrays like 1, 2, 2, 3, 3, where two elements share the same frequency, should correctly return false. These edge cases highlight the importance of our algorithm's logic and its ability to handle different scenarios effectively. Now, let's discuss why we use specific data structures in this algorithm. The dictionary frequency_map is particularly useful because it allows us to count the occurrences of each element in O(n) time, where n is the size of the array. Each insertion or update operation in a dictionary is O(1), making it highly efficient. Similarly, the set scene_frequencies is ideal for tracking already seen frequencies because it allows O(1) membership checks. This is much faster compared to using a list, which would require O(n) checks for duplicates. When we analyze the time complexity of the entire algorithm, counting frequencies takes O(n), and checking the uniqueness of frequencies takes O(k), where k is the number of unique frequencies in the array. Since k is always less than or equal to n, the overall time complexity is O(n). For space complexity, storing frequencies in frequency_map requires O(k) space, and tracking scene frequencies in scene_frequencies also takes O(k). Therefore, the overall space complexity is O(k). These choices for data structures and the resulting complexities make the algorithm both efficient and scalable. Let's walk through an example to see how the algorithm works in practice. Suppose we have the input array ARR equals 1, 2, 2, 3, 3, 3. First, we build the frequency_map dictionary by counting the occurrences of each element. The result is frequency_map equals 1, 1, 2, 2, 3, 3, where 1 occurs once, 2 occurs twice, and 3 occurs 3 times. Next, we check the uniqueness of these frequencies. We start with the frequency 1 and add it to the scene_frequencies set, resulting in 1. Then, we process the frequency 2 and add it as well, making scene_frequencies equals 1, 2. Finally, we process the frequency 3 and add it, resulting in scene_frequencies equals 1, 2, 3. Since there are no duplicate frequencies, we return true, indicating that all frequencies are unique. This example demonstrates how the algorithm correctly identifies unique frequencies in a straightforward case. Now, let's consider another example to see how the algorithm handles a case where frequencies are not unique. Suppose the input array is ARR equals 1, 2, 2, 3, 3. First, we build the frequency_map dictionary, which results in frequency_map equals 1, 1, 2, 2, 3, 2. Here, 1 occurs once, while both 2 and 3 occur twice. Next, we check the uniqueness of these frequencies. We start with the frequency 1 and add it to the scene_frequencies set, resulting in 1. Then, we process the frequency 2 and add it, making scene_frequencies equals 1, 2. However, when we encounter the next frequency 2, we find that it is already in scene_frequencies. This means we have a duplicate frequency, so we immediately return false. Finally, the optimized implementation of the algorithm is shown here in Python. The code is concise and directly follows the algorithm's steps, making it easy to understand and apply to any input array. The solution begins by defining a class solution and implementing the method unique occurrences to solve the problem. The function takes a single parameter ARR, which is the input list of integers. Step 1. Frequency calculation. The first step involves computing the frequency of each number in the array. This is achieved using a dictionary frequency_map. The loop iterates through each number in the array, updating the dictionary to count occurrences. The get method ensures that if the number is not already in the dictionary, it starts with a count of 0. Step 2. Verify unique frequencies. Next, we need to determine if all frequencies are unique. A set scene_frequencies is used to store already encountered frequencies. The code iterates through the values in frequency_map, i.e., the frequencies. If a frequency is found in the set, it means a duplicate frequency exists, so the function immediately returns false. Otherwise, the frequency is added to the set. Return result. If the loop completes without finding duplicate frequencies, the function returns true, indicating all frequencies are unique. This implementation is efficient, with a time complexity of O(n), where n is the length of the input array. The space complexity is also O(n), considering the space used by frequency_map and scene_frequencies. It handles edge cases such as empty input or arrays with all identical elements effectively. This is the Java implementation of the unique number of occurrences problem, LeetCode number 1207. The logic mirrors the provided Python implementation. We use a hash map to count the frequency of each number, and a hash set to ensure the frequencies are unique. Key differences include explicit type declarations, use of Java's collections framework, and Java's structured class-based approach. The problem we're tackling here is to determine whether the number of occurrences of each unique element in an array is unique. What this means is that we need to ensure that the frequencies of all distinct numbers in the array do not repeat. For example, if we look at the input array 1, 2, 2, 1, 1, 3, our goal is to check whether the counts of each number are all different. Let's break it down step by step. First, we initialize an empty dictionary called frequency_map to keep track of how many times each number appears in the array. Then, as we traverse the array, we update the frequency of each number. After processing all the elements, our frequency_map ends up looking like this: 1, 3, 2, 2, 3, 1. This tells us that the number 1 appears 3 times, 2 appears twice, and 3 appears once. This frequency map is the foundation for the next step of the solution. Now that we have our frequency map, the next step is to check whether all the frequencies are unique. To do this, we create an empty set called scene_frequencies to track the frequencies we encounter. We then go through the values of our frequency_map, which in this case are 3, 2, 1. As we iterate, we add each frequency to the set. First, we add 3, then 2, and finally 1. After adding all the frequencies, the set contains 3, 2, 1. Since there are no duplicates in this set and all frequencies are distinct, we can confidently conclude that the condition is met. Therefore, we return true, indicating that the occurrences of the numbers in the array are unique. Let's consider another example to see how this process handles a case where the frequencies are not unique. Suppose the input array is 1, 2, 2, 1, 1, 2, and our goal is once again to determine if the frequencies of the numbers are unique. We start by initializing our frequency underscore map and traversing the array to compute the frequencies. As we process each element, we update the map like this: frequency underscore map 1 equals 1, frequency underscore map 2 equals 1, and so on. By the end, our frequency map looks like 1, 3, 2, 3. This shows that both 1 and 2 appear 3 times each. Next, we check for unique frequencies. The values of frequency underscore map are 3, 3. As we add these frequencies to the scene underscore frequency set, we first add 3, but when we try to add 3 again, we find that it's already in the set. This indicates a duplicate frequency. Because of this, we return false, as the condition of unique occurrences is not satisfied. Finally, let's look at a simpler example where the input array is 1, 2, 3, 4, 5. Here, each number is distinct, so their counts should naturally be unique as well. We start by initializing the frequency underscore map and computing the frequencies. As we traverse the array, we find that each number appears exactly once, resulting in the frequency map 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. Next, we check the values of the frequency map, which are 1, 1, 1, 1, 1. Since all these frequencies are the same, we quickly see that they are not unique. However, we can now summarize the solution. By computing the frequency of each element using a dictionary and verifying uniqueness with a set, we achieve an efficient way to solve the problem. This approach ensures that we can determine if the occurrences of numbers in any array are unique. To analyze the time complexity of this solution, we can break it down into 2 main steps. First, we construct a frequency map by iterating through the array ARR. For each element, we either insert it into the dictionary or update its value. Since dictionary operations like insertion and retrieval have an average time complexity of O(1), this entire step takes O(n), where n is the size of the array. Next, we check for unique frequencies by iterating through the values in the frequency map. For each frequency, we perform a membership check in a set and potentially add it to the set. These set operations are also O(1) on average, and since there are at most n unique frequencies, this step is also O(n). When we combine both steps, the total time complexity of the solution is O(n) plus O(n), which simplifies to O(n). Now let's evaluate the space complexity. The frequency map, frequency underscore map, stores the frequency of each unique element in the array. In the worst case, where all elements in the array are unique, the map will contain n entries. Since each entry consists of an integer key and value, this requires O(n) space. Similarly, the set used to track scene frequencies, scene underscore frequencies, can store at most n unique frequencies in the worst case scenario, which also requires O(n) space. Beyond these data structures, the algorithm uses a constant amount of auxiliary space for variables like number and frequency during iteration, which is O(1). When we add these components together, the overall space complexity becomes O(n) plus O(n) plus O(1), which simplifies to O(n). Let's compare this optimized approach with a brute force solution. In a naive implementation, we might count the occurrences of each element using nested loops, which would take O(n) squared time if no hash map is used. Then, we would compare frequencies for uniqueness, which could take O(m) squared time 4m unique elements. This brute force approach results in an overall time complexity of O(n) squared and a space complexity of O(1) if no additional data structures are utilized. However, the optimized solution improves significantly by using hash maps and sets for constant time operations. It reduces the time complexity to O(n) while maintaining an O(n) space complexity. This trade-off between time and space is much more efficient and practical for real-world scenarios. Finally, let's consider the best, average, and worst-case scenarios for this solution. In the best case, where all elements in the array are the same, the frequency map will only contain one key, and the set for scene frequencies will have just one entry. Even in this case, the algorithm still processes all n elements in the array, so the time complexity remains O(n). In the average case, for a random input, the number of unique elements and frequencies will vary, but the linear processing of the array and the constant time operations of the hash map and set keep the complexity at O(n). In the worst case, where all elements in the array are unique, the frequency map will have n keys, and the set will also contain n entries. Both loops process n elements, so the complexity is still O(n). Mathematically, we can confirm this. Iterating over the array to compute frequencies takes O(n), and checking for unique frequencies also takes O(n). Combining these steps, the total time complexity is O(n) plus O(n), which simplifies to O(n). This demonstrates that the solution is optimal for this problem. When working on this problem, there are some common mistakes you need to watch out for. First, failing to account for edge cases, such as empty or single-element arrays, can lead to runtime errors or incorrect results. For instance, an empty array should automatically satisfy the condition of having unique frequencies, but if you miss this check, you may encounter issues when trying to access elements that don't exist. Another mistake is incorrectly counting frequencies. Using an inefficient or error-prone method, like manually iterating instead of leveraging tools like Python's counter or a hash map, can introduce bugs and inefficiencies. You should also consider whether the input allows negative or non-integer values. Assuming all inputs are positive integers might cause logical errors if this assumption is incorrect. Finally, avoid using nested loops unnecessarily. A naive implementation might compare frequencies with nested loops, which results in O(n) squared performance. Instead, you can use a hash set to efficiently check for duplicates in O(n). Paying attention to these pitfalls will make your solution both robust and efficient. Misinterpreting the problem requirements is another common mistake. For example, some might mistakenly check if the array elements themselves are unique, rather than their frequencies. This misunderstanding can lead to solving the wrong problem entirely, so always double-check the problem statement to ensure you're addressing the right goal. In interviews, focus on clarity and correctness first. It's better to present a simple, correct solution before attempting optimizations. For frequency checking problems, starting with a brute force approach can help you organize your thoughts and demonstrate your understanding. If prompted to optimize, discuss trade-offs, explain why a hash map approach with O(n) complexity is preferable to the inefficiency of nested loops with O(n) squared complexity. Additionally, explicitly discussing edge cases, like empty arrays, arrays with identical elements, or cases involving large value ranges, shows interviewers that you've thought through the problem thoroughly. Finally, modularizing your code by using helper functions, for example, one dedicated to frequency counting, can keep your solution clean, organized, and easier to debug. If you want to practice similar problems to strengthen your skills, there are several related LeetCode problems worth exploring. For example, LeetCode 217 contains duplicate, shares the concept of detecting duplicates, but it focuses on array elements themselves rather than their frequencies. Another example is LeetCode 242, valid anagram, which requires frequency counting of characters in a string to determine if two strings are anagrams. This builds on the same skill set used in the current problem. You can also look at LeetCode 451, sort characters by frequency, which combines frequency counting with sorting, introducing a common variation of this type of problem. And finally, of course, there's LeetCode 1207 itself, unique number of occurrences, which asks you to determine whether the frequencies of numbers in an array are unique. Each of these problems reinforces key concepts like frequency counting, duplicate detection, and efficient handling of data structures. There are several approaches you can use to solve this problem, each with its own trade-offs. A brute force approach involves first counting frequencies with a hash map and then using nested loops to compare all frequency values. While this method is simple to understand and implement, its time complexity is O(n) squared, making it inefficient for larger inputs. A more optimal method combines a hash map and a hash set. In this approach, you count frequencies with a hash map and then store the frequency values in a hash set to check for duplicates. If you detect a duplicate frequency, you can immediately return false. This method has a time complexity of O(n) and is generally the most efficient solution, though it does use slightly more memory. Another less common approach involves sorting. Here, you count frequencies using a hash map, then sort the frequency values and check for duplicates in a single pass. While this approach is easier to implement than the hash set method, its time complexity is O, n log n, which makes it less efficient for very large datasets. Each approach has its own strengths and weaknesses, so it's important to choose the one that best fits the problem constraints. In some situations, you might consider using alternative data structures to solve the problem. For example, you could use a balanced tree to store and manage frequency values. This approach might be appropriate if the problem requires frequent updates or queries on the frequency data. However, the complexity of such an approach depends on the specific data structure used. For instance, balanced trees often have an O, n log n, complexity for operations, which makes them less efficient than a hash map and hash set combination in most cases. Additionally, implementing custom data structures is often overkill unless the problem constraints specifically require it. While these approaches can be interesting to explore, they're generally not the most practical solution for LeetCode problems like this one. Instead, sticking to a hash map and hash set setup will typically give you the best balance of simplicity and efficiency. Great job! We've successfully solved problem number 1207 and learned how to effectively use hash maps for frequency counting. Remember to practice similar problems to solidify your understanding. Thank you for watching, and don't forget to like and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!